Okay, so what are common things that we do with enolates? One is enolate alkylation. Okay, let's draw a ketone. Again, I'm going to my very simple ketone. Turns out for enolate alkylation, we're going to make an enolate. And then we're going to add an alkyl halide. This is basically going to do an SN2 reaction. So here's our ketone. I'm going to draw in our alpha hydrogen. And to do enolate alkylations, we need to control what's happening when we form the enolate. And the way we get control in enolate formation is we use a really strong base. We don't have to worry about the position of the equilibrium because it basically is completely to the right towards the enolate formation. So LDA is basically a base. It's going to pluck off that hydrogen and give us our enolate. And lithium is our counterion. And so that's the first step. So we've done that. Make the enolate. We have made our enolate. Now typically an enolate is a nucleophile like carbon. So it's a carbon nucleophile. And we've chosen to draw the resonance form that emphasizes having the charge on the carbon instead of the one that puts a negative charge on the oxygen. So step 2. Then, so that means step 2, we're going to add an alkyl halide. So I'm going to choose some generic alkyl halide, specifically a bromide. Note that alkyl halides here are typically primary halides. We'll talk about that in just a second. So, as a nucleophile, this carbon comes in, and we're just doing an SN2 reaction. So this is a strong nucleophile, kicks out the halide, and we do an SN2 reaction. Now, it's very easy to drop a carbon when you do this. So here's our alpha carbon, here's our alpha carbon, and I'm going to put a star next to the carbon in our alkyl halide. Don't forget that carbon. For some reason, people just tend to drop a carbon out. The carbon is still there. So what we've done is we've made a new carbon-carbon bond. And carbon-carbon bonds, historically speaking, were not the easiest things to make. So when people discovered you could alkylate enolates, it's a very easy way to connect two organic molecules and make larger structures. So this is historically a really important reaction. Okay, 2 features I want to talk about. 1, the base. Why LDA? Well, think if you use sodium hydroxide or some other relative like sodium, like an alkoxide. Remember, in that case, we set up an equilibrium when we form the enolate. And if we use one of these weaker bases, we have mostly unreacted aldehyde or ketone and unreacted base. So if we tried to form the enolate with a weak base, we'd have mostly starting materials. Well, then when we add the alkyl halide, we could have sodium hydroxide reacting with our halide. And we might see E2 reactions. We might see these bases acting as nucleophiles and doing SN2 reactions. We'd see side reactions. So that's why we tend to favor LDA for these processes. So question number 2. Why a primary halide? Well, as it turns out, even though enolates are SN2 nucleophiles, they are not one of our really classic strong nucleophiles. They're not azide, they're not cyanide, and they're not sulfides. Therefore, when we have strong nucleophiles, which aren't our super strong or really excellent nucleophiles, we are limited to the primary halides. If you use the secondary halide, the halide is now more hindered, and our enolate, instead of acting as a nucleophile, might act as a base, and we're going to tend to get E2 reactions. So all the rules that we learned about SN2 reactions still hold up, even though we've introduced this new nucleophile, the enolate. But the rules hold up. The enolate is not one of the great nucleophiles, and only our great nucleophiles will do SN2s on secondary halides. In this case, it's not a great nucleophile. We're going to start seeing E2 reactions. So to alkylate and enolate, we need to use our strongest base, LDA, and we must use a primary halide.